In this video, I'd like to do some example problems so that you have a better sense of how we would use some of the equations, especially for uniform circular motion. Okay, rotation example number one. I think it's the only rotation example I have, and it's really here just to emphasize how rotation is different from revolution. Revolution is one object going around another object. So, for example, the Earth going around the Sun or the Moon going around the Earth. And then rotation is an object spinning. So we will sometimes talk about rotation for things like a figure skater spinning in place, or in this case, the period of rotation of the Earth in seconds. So part A there, what is the period of the rotation of the Earth? I know that's 1 day. Part A is just asking for unit conversion to seconds. Part B, what is the angular velocity of Earth? And then the hint, what are the units? And then part C, given the radius of the Earth is 6.4 times 10 to the 6th meters at the equator, what is the linear velocity at the Earth's surface? Part C is really asking, if you stand in place at the equator, then how fast will you be moving just by virtue of the fact that the Earth will spin you all the way around once in 24 hours? How fast will you be going in terms of meters per second? So let's start with A. I want to be able to view the Earth in a way that lets me really identify the rotation. So this image is a really good one to be able to identify that if you're standing anywhere on the planet and you just stand still, the Earth will turn all the way around once in 1 day. That's 24 hours. That's unit conversion would give me 1440 minutes, and that's 86,400 seconds. And I really want to emphasize that's true no matter where you are. If you stand on the North Pole and don't move for 24 hours, the Earth's rotation would cause you to spin in place in that 24-hour period of time. And if you're anywhere else, if you're, for example, in Virginia, then you trace a path that's once around the planet, but from this perspective that we're looking down at the North Pole, you would see that that person is not moving as much as a person who is, for example, in Florida. Just by standing still, a person in Florida is moving a larger circumference as the Earth spins on its axis. And of course, the largest circumference is the equator. If you're standing still on the equator, you do a full circumference of the Earth every 24 hours, just by virtue of standing still. So part B, what is the angular velocity of the Earth? Angular velocity is talking about how many radians per second you're traveling. So the angular velocity of the Earth should just be that it turns 360 degrees in 1 day, but we don't want it in units of degrees, and we don't want it in units of days. We want it in the metric system base units, the SI base units. So rather than say 360 degrees, I would say the Earth does one complete turn, that is 2 pi radians. And the amount of time, instead of saying per day, I would say per 86,400 seconds. And the only reason I would ever refer to the Earth's angular velocity as 7.27 times 10 to the negative 5th radians per second, instead of saying it rotates once per day, is because I was specifically asked to put it in metric units. If you were to say 1 rotation per day, that's saying the same thing, just not in base units. The reason part B is being asked here at all is really so we can use that value in part C. There's a couple ways you could do part C. One is that you could calculate the circumference of the planet at the equator and then divide that by our answer to part A, and you would get an answer of meters per second, which is what we're looking for. Or you can say that the tangential speed, or the instantaneous speed for an object is equal to r times omega. So that's what I'm going to do here. This is really useful for determining, for example, the linear speed of a fly standing on a record, like we saw an image of in the previous video, or for a person standing on the surface of a planet as the planet spins, as long as you know how far they are in a straight line from where they are into the planet to the axis. So if the radius is given and the angular velocity is our answer to part B, then the linear speed is the 6.4 times 10 to the 6th meters times the 7.27 times 10 to the minus 5th radians per second, and that gives me 465 meters per second, which is over 1,000 miles an hour. That is as it says here, about 1675 kilometers per hour. And if you want to check that, you can calculate how long it would take you to travel the circumference of the Earth at that speed, and you'll come up with that it's about 24 hours. In fact, it should be exactly 24 hours. Okay, let's take a look at another example, and this one is not rotation. In fact, the next three are not rotation, but instead are uniform circular motion. What is the magnitude of the centripetal acceleration of a car following a curve of radius 500 meters and traveling at a speed of 25 meters per second? This drawing is clearly not to scale because 500 meters is a pretty big center of rotation. And then what is the magnitude of force necessary to make this 900 kilogram car manage this turn? Notice they don't give us the mass until the second part of the question. That's because I don't need the mass for the first part of the question. The acceleration that the car will undergo if it's traveling at a constant speed in a circular motion is given by the equation v squared over r, which is a known equation for objects traveling in a circle. The acceleration in a circle is v squared over r. V is the speed, the instantaneous velocity, and r is the radius of the circle. So this is a very straightforward calculation, and I get that it is 1.25 meters per second per second. What is the magnitude of force necessary to make this 900 kilogram car manage this turn? Well, Newton's second law still applies. So the force necessary to make that happen is equal to ma, where a is, because we're going in a circle, v squared over r. That should seem really easy to do, and I will tell you right now it is, but one of the things that sometimes happens with students is if you get asked this second question and you haven't first been asked the first question, you have to know to put in the centripetal acceleration as your acceleration. A nice reminder of that would be the phrase constant speed. Anytime that it is either explicitly stated or implied, like in this question, it's kind of implied. It's at a speed of 25 meters per second, and it's the wording of that sort of suggests that it's not speeding up or slowing down. So that should jog your memory that, oh yeah, it's traveling in a circle at this constant speed. My equation for the acceleration is therefore no longer delta v over delta t, it's v squared over r. I'd like to talk a little bit about the force that is making this car go around in a circle. This is an image of a car that's the same color but turning in the opposite direction as the problem we just did. And this image comes from your textbook, the OpenStax textbook. And the question it's asking now is, what is the minimum static coefficient of friction between the tires and the road? I want to emphasize that friction is the reason that the car would be able to make the turn. I think I mentioned in the previous video that if this car were driving down an icy road and had no friction between the tires and the road, it would travel in a straight line in the direction that the V is. That's how cars go off the road. You're not able to make the turn. Our free body diagram is drawn here with the gravitational force down and the normal force up. And the only force in the plane in which the car is moving, it's not accelerating up and down, it's just changing its direction in this surface of the ground plane. And the only force acting on it in that direction is that force of friction. Well, we know that the centripetal force from the previous slide is 1,125 newtons. We also know that the centripetal force in this case is friction. And so what I would do is take that centripetal force we calculated, the 1,125 newtons, and I would set it equal to what I know friction is, which is mu times the normal force. In this case, the normal force is equal to mg because my car does not have anything else going on in the y direction. The textbook talks about banked turns, and that changes what's going on in the y direction. That's a really interesting concept. We're not going to get a chance to spend time on it. I'm not going to put something like that on the test. So I definitely think it's interesting to check out, but if you're short on time, that would be something you could gloss over. I will say that in this case, since you know that the coefficient of static friction is equal to the friction force divided by the normal force, and you know the friction force was calculated that is the centripetal force, it's 1125 newtons, and you know the normal force is the mass times g, then you can just put all those numbers together and calculate that this coefficient of static friction is 0.128. I specifically wanted to include this example question to talk about the static friction. I frequently have students who are uncomfortable with the idea that the car is moving, and I'm calling it static friction. So let's take a moment to talk about that. When a tire is spinning and not going anywhere, then there's no friction between it and the ground. What allows a tire or a wheel to go somewhere is when it has friction with the ground. Specifically, it has to have static friction with the ground because the point of the tire that is in contact with the ground isn't sliding or slipping. So if you've ever had a bike or a car or something like that you're riding along and then you slam on the brakes and it skids, that skidding is actually an instance of kinetic friction because now your bike or car tire isn't turning and it's just sliding across the ground. That's very different from what's happening when it's rolling. I don't want to get into a situation where I'm trying to trick you with this, but I want to emphasize that that is a static point on the wheel, is at any given moment the part of the wheel that's in touch with the ground. That's why if you were to put LEDs on bike wheels and take an extended time photograph of it, it looks like this. You get to see that at each of those points where it is touching the ground, that's a point where the edge of the wheel that had the LED touched the ground and for a moment there was not moving in that arcing pattern. Okay, our second example of uniform circular motion. A bucket of water is swung in a horizontal circle. The bucket and the water have a combined mass of 4 kilograms. We're going to assume that the string is massless in all of our questions, unless we're specifically told otherwise. What period of rotation is needed to keep the string at an angle of 10 degrees from horizontal? So the period of rotation is a measurement of time. So it's asking me how much time should the bucket take to make one full loop, one full circumference. And it says, hint, how fast will the bucket be going? Okay, how fast it will be going is a measure of V, and of course this is a circular motion problem, so I should be thinking about the fact that the acceleration of the bucket will be V squared over R. And I'm still not exactly sure what to do first, so what do we do when we're not sure what to do? That's a good time to draw a free body diagram. The free body diagram of the bucket will look like this. The force of gravity is pulling down on it, and there's a force of tension in the rope pulling on it up. And in the particular moment of the drawing, it's sort of pulling up and to the right. That force of tension in the rope does have a Y component that's necessary to counteract the force of gravity. It also has a X component that would, from our perspective outside of the circle, would change direction constantly, but is always pointed to the center of the circle. So the X component is always the radial component. That is the centripetal force, is the X component of the tension. The tension is serving two purposes here. One, keeping the bucket from falling down, and two, making the bucket go in circles. Well, it told us in the problem that there's an angle of 10 degrees from the horizontal that the string is. So the string is this red vector, and those two angles that I drew right there are the two angles. You could pick either one of them. They're the two angles that express that our force of tension is not horizontal, it's some degrees from horizontal. I know that in the X direction, the net force, which is the tension X component, is equal to the mass times the acceleration in the X direction. And I know that based on the reading of the question, that the acceleration in the X direction is centripetal. So I would replace the A in the X direction with a V squared over R. So the tension in the X direction equals mv squared over R. The V squared, because I'm trying to find out how fast the bucket is going, that was my hint, is then force of tension in the X direction times the radius over the mass. They gave us the radius in the problem, and they gave us the mass of the object going around in circles. I don't know what the tension in the X direction is. But I do know that that angle is 10 degrees. And I do know that the tangent of that angle is the force of tension in the Y direction over the force of tension in the X direction. That's useful because I can put tangent 10 degrees into my calculator and turn it into a number, which means if I know the force of tension in the X or the Y, I can use this expression to determine the other. And I'm going to suggest that I do know the force of tension in the y. So the force of tension in the x direction is equal to the force of tension in the y direction divided by tangent 10 degrees. And looking at the free body diagram, the force of tension in the y direction plus the force of gravity must equal 0. And the force of gravity, of course, is downward. So force of tension in the y direction must be equal to the force of gravity. They're just in opposite directions. And add up to 0 because I know that the bucket is only accelerating in a circle. It's not moving up or down in the problem. So that means that the force of tension in the x direction is 222.3 newtons because I substituted in the mass times g as the force of tension in the y direction. Now that I know the force of tension in the x direction is 222.3 newtons, I can substitute that back in to the equation I was working with, along with the value for the radius of the circle and the value for the mass of the bucket and water. And I get, therefore, that the speed of the bucket is 7.5 meters per second. That's not what they asked me, though. That was the hint. They said that if I could determine how fast the bucket was going, I could use that to determine how much time it takes to go around. I know that the speed of the bucket, even though it's going in a circle, the speed is still distance over time. And specifically because it's going in a circle, I know the distance is the circumference, 2 pi r. We want to be careful not to put in something like pi r squared. That's the area of a circle. Anytime you're in doubt, it's always good to double check yourself. So rearranging this for time, we get that the period that it takes the bucket to go around once at this speed is 2 pi times the radius that was given, which was 1.0 meters, divided by that speed that we just calculated, the 7.5 meters per second. And so therefore that time is 0.84 seconds. The bucket has to go around every 0.84 seconds in order for that angle to be 10 degrees. And if you go around in less time than that, we could show that that means that the angle would get less than 10 degrees. Our fourth and final example for this video is actually the third example of uniform circular motion, and that is to determine the force of attraction between the Earth and the Moon, given the Moon's mass and the mean distance from the center of the Earth to the center of the Moon. So the Moon is going around in circles around the Earth. That means if it's going around in circles, it's still uniform circular motion. We get to use the equations that we've been working with. Let me go ahead and start with the free body diagram of the Moon, though. That's my free body diagram of the Moon. I'm looking at the drawing here, and I'm seeing that the Moon is to the right of the Earth, and so there's a gravitational attraction in this direction that I've drawn here. And if you're tempted to say that shouldn't it be down, I'm going to tell you it is down. Down is the direction that gravity pulls things towards the Earth. Even something as far away as the Moon, you could refer to the Earth as down, because that's the direction gravity is pulling. There's no other force acting on the Moon other than things like, well, I mean, the gravity of the Sun pulls on the Moon and so forth. We're actually going to get into that a little bit in the next video. But for this problem, the only interaction that the Moon is experiencing that we're talking about at all is the gravitational attraction from the Earth. That means that the force from the Earth to the Moon, or between the Earth and the Moon, is the force that is acting radially or centripetally on the Moon. If you didn't know it was gravity, you could still say that the force of the Earth acting on the Moon is the mass of the Moon times the velocity of the Moon, the instantaneous velocity of the Moon squared, divided by the radius of orbit. Do you know how fast the Moon is going around the Earth? You could certainly find that because the speed of the Moon going around the Earth is going to be distance over time. So it's the circumference of its orbit divided by the time it takes to go once around. And the radius of the orbit was given to us. The time to go once around was not, so I looked that up. It's 27.3 days. I'm going to want that in seconds, which is the base unit for the metric system. So I convert that to seconds, and I substitute in the distance between the Earth and the Moon. And I've got these big numbers now. The circumference is 2 pi times 3.84 times 10 to the 8th meters. And then the time to go once around the Earth is about a month. That's this 2,358,720 seconds. that gives me that the moon is actually traveling a little over 1,000 meters per second in its orbit around the Earth. I can take that speed of the moon and put it back into that red equation up there and say that the force that the Earth exerts on the moon to make it go in a circle is the mass of the moon, which was given to us in the problem, times the speed of the moon, which we just calculated, squared, because the acceleration in a circular motion is v squared over r. And then our r goes in again. That's our radius of our orbit. And so this all comes out to 2.0 times 10 to the 22nd newtons, which is a really incredibly large force. But then again, we're talking about how much force is acting between the moon and the Earth, and it should be a really, really large number. I wanted to use this example to point something out. You might have thought that you could just take the mass of the moon times g, and g is 9.8 newtons per kilogram, and this looks like a much easier calculation, and you get a very different answer, though. This is an answer that's 36 times too strong, and that is because you can't use lowercase g unless you are on or very close to the surface of the Earth. And the moon is not very close to the surface of the Earth. It's like 60 Earth radii away from the surface of the Earth. So g is only applicable when you are talking about objects on or near the surface of the planet. And anytime you're talking about how strongly things are attracted to the planet when those things are not on the planet, we're going to have to deal with that a different way. And that's actually what our next video will be.